Hi everybody, welcome back. This is Chapter 4, Unit 4, Lesson 6. And today we're in Section 6. We're going to talk about artificial radioactivity, or how we make things that are stable, unstable. We all know that can happen in our life, right? You'll be sitting there, everything's fine, and then, something sets you off. Something makes you unstable. And that's the same thing with isotopes. We can take stable things, and basically what we do is we bombard them with high energy particles. It could be any particle like you were doing in the lab, like with alpha particles or neutrons or whatever, and that makes the nucleus unstable, and then it spews. So we can produce radioactive isotopes by bombarding stable isotopes with high energy particles. And those particles could really be anything. They could be alpha particles, they could be neutrons, they could be protons, etc. Okay? When this happens and we make it a stable isotope unstable, well then it spews, it transmutates, and it turns into someone new. And we call that artificial transmutation. Okay? So artificial transmutation is when we make a nucleus undergo decay. Christian.
I could smell it was all the way down the wall.
So it's when you make a nucleus undergo decay. Sorry, I had to beat Christian down. Okay, so it's when we make a nucleus undergo decay. And I'm just kidding, for the record, in case, there's anybody important that's watching this other than my students. I really didn't beat him. Look, he's right over there. He's perfectly safe and fine. Okay.
I like matches.
All right. So it's when we make a nucleus undergo decay, and here's what it looks like. You can always tell, you can recognize this. Because there will be two reactants. There will be two things to the left of the arrow. Okay? So let's say we took, aluminum 2713, and we bombarded it with a neutron. Well, that would make that aluminum nucleus unstable, and then it could spew. And it could turn into different things, but let's say it emitted an alpha particle, and it turned into, 28, so this would be 24 sodium. Okay? So in this example, aluminum transmutates into sodium. It transmutates into sodium, but we make it happen. We add the neutron, which makes the nucleus unstable, and then it splits, and then it spews. Okay? Contrast that to natural transmutation, just for the record. And in natural transmutation, you have something that's radioactive, like carbon-14, and it just decays all by itself, right? It is a beta emitter, and it turns into nitrogen, okay? Natural transmutation, there's only one thing to the left of the arrow. Artificial transmutation, there are two things to the left of the arrow. Okay, in all nuclear reactions are different than ordinary chemical reactions because they involve reformation of the nucleus. And here's what's interesting when you reform the nucleus. If you have a proton, which weighs 1 AMU, and you have a neutron, which weighs 1 AMU, when you put them together to make the nucleus, what would you predict the mass of that nucleus to be? Did you say 2? Because 1 plus 1 equals 2? Except in nuclear reactions, 1 plus 1 does not equal 2. I know, chemistry really doesn't make sense sometimes. But in this nuclear reactions, when you make the nucleus, some of the mass of the particles is actually released as energy. Okay? Some of the mass is released as energy. And we call this mass defect, where this nucleus should weigh 2, but the nucleus actually weighs less than 2 AMUs. Not a lot less, just a teeny, 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 tiny bit less. So mass defect is the idea that during nuclear reactions, some mass is lost as energy. And there's actually a relationship between the amount of mass that's lost and how stable this nucleus is. And that is this. The more mass that's lost, right? So that would mean the greater the mass defect, the more stable the nucleus. Okay? So the more mass that's lost, the more stable the nucleus. And the reason for that is in letter D. Because if I wanted to take this nucleus and break it back apart, I would have to put in all the energy that was lost. So the more energy that's lost, the more energy that I have to put in to break apart the nucleus. And that is what binding energy is. It's the energy needed to break the nucleus back into protons and neutrons. And it's equivalent to the energy released when the nucleus is formed. So what makes nuclear reactions special? What makes nuclear reactions different than ordinary chemical reactions is that mass is converted to energy. And I know you've seen this before. We can actually measure the amount of energy if we know the mass that's lost. And there's a very famous equation made by a very famous scientist that allows us to calculate the energy that's released. You will not have to do this at this level, but I want to tell you that this equation is how we can calculate the energy that's released when the mass is lost. That mass happens to be traveling at c, which is the speed of light. It's traveling really fast. So this is the mass that's lost. E is your energy. And c is a constant. It's the speed of light, 3 times 10 to the 8th. Which you have to square. So even if m is a super duper duper small number, you're going to get a lot of energy released. In fact, nuclear reactions produce 3 billion times more energy than ordinary chemical reactions. There are 2 main types of nuclear reactions that we're going to talk about in more detail tomorrow, but I'd like you to write these down. They are fission with 2 S's, which is the splitting of an atom, and reformation of atoms. So you're reforming nuclei, which is how you get the energy lost. And fusion with a U, which is the uniting. It's the opposite of nuclei. So this is the fission is the splitting of a nucleus. Fusion is the uniting of nuclei. And we'll talk about these in more detail tomorrow. Okay? So I'd like you to practice saying those, fission and fusion, because they look the same and it is kind of confusing, and maybe come up with your own way to remember them. For example, I had a student say, you have to split the worm to go fission. Fission, like fishing, you have to split the worm and it's the splitting of a nucleus. I don't care. I like the S's for splitting and the U's for uniting, but whatever you need to do so that you remember that, because I understand it can be confusing. I will check your notes tomorrow. I apologize for Christian and his matches, but it is his birthday, so wish Christian a happy birthday. And we'll see you tomorrow in class where we'll talk more about fission and fusion. Good night, everybody.